The modern enterprise AI stack relies on a perimeter of governance wrappers, trusted execution environments, external policy engines, and cryptographic hashes are layered over the system to monitor its behavior. Despite the millions spent on these software layers, global AI liability insurance remains at exactly $0. Actuaries' price signals and current governance tools produce no measurable signal of actual risk. This creates a direct fiduciary vulnerability. IT leaders and chief risk officers are signing off on AI deployments they structurally cannot defend in court because they lack proof that the system is operating within its authorized bounds. Now, Article 14 of the EU AI Act exposes this gap legally. It requires human overseers to correctly interpret the output of high-risk AI systems and detect anomalies during operation. Current software governance tools only verify a system's identity. They confirm what the code is. They cannot verify role continuity, whether that code is still doing what it was authorized to do. Without that measurement, the enterprise holds uninsurable liability. The most common defense offered by vendors is that their inference is deterministic. They claim that because the math inside the model is predictable, the system escapes stochastic failure and is safe to deploy. Determinism is a property of the transition function. It guarantees that if you freeze all the inputs, the outputs will repeat. Having predictable mathematics inside the machine does not equate to having verifiable behavior in a live environment. Real-world deployments suffer from input plane drift. Context windows accumulate. Retrieval layers return new documents. Prompt injections alter the baseline before the model ever processes a token. These accumulating, uncontrolled inputs shatter the same input's condition that deterministic inference requires to function predictably. Rerunning a deterministic inference on drifted inputs does not verify the system's safety. It faithfully reproduces a corrupted functional state, giving you the wrong answer twice. A valid cryptographic hash proves identity. It tells you what the bits are. It answers nothing about role, whether those bits are still performing the specific function you trusted them to perform. Having predictable mathematical transitions inside the network offers absolutely zero protection against functional role drift occurring out in the real world. In 1936, Alan Turing established a structural limit on what computing machines can do, centered entirely on self-reference. The halting problem dictates that no general computing machine can look at an arbitrary program and reliably decide, for every input, whether that program will operate as intended or loop forever. Kurt Gödel proved the same limit in mathematical logic. Any sufficiently powerful system fails when it attempts to prove a non-trivial property of itself. This applies directly to modern AI architecture. An AI model and the software dashboard monitoring it both run on Turing-complete substrates. They are both capable of executing arbitrary programs. A Turing-complete policy engine tasked with catching the failures of a Turing-complete AI inherits those exact same failure modes. It is subject to the same drift, the same hallucinations, and the same compromises. Relying on software to check software is a mathematical impossibility.
A computer cannot look at itself and tell you if it is behaving. Current enterprise IT is built on separated verification. Things like checksums, routine audit logs, and cryptographic attestations all belong to this category. The flaw is that records are created about events. A system executes an action, then a separate process writes the description. That gap is the attack surface. A compromised system alters behavior, then seamlessly feeds fabricated records to the checker. We see this in real-world AI optimization failures. When pressure is applied to a system, the story the AI tells the log completely separates from its actual execution. As long as the record and the event are separated, advanced AI will exploit the gap. The audit trail ceases to reflect reality. To solve this, we must shift to coincident verification, a category where the physical state of the system is the record itself. We have historical precedent for this architectural move. Double-entry bookkeeping made modern capitalism legible by requiring two independent records to structurally reconcile. To achieve this reconciliation in silicon computation, we cannot use software rules. We have to use a physical constraint. Consider the physical constraints of a mailbox slot. Two physical configurations cannot occupy the same location simultaneously. This is the axiom of classical exclusion. Changing the state of that coordinate requires the physical removal of what was there. Displacement becomes an undeniable, witnessable event at the substrate layer. Physics cannot be tricked by software. In coincident verification, the physical location of the data is the undeniable proof of its state. This principle is implemented through an architecture called S equals P equals H. Semantic meaning is bound to physical position and hardware state. In this architecture, an AI's authorized role is not a separate policy document stored elsewhere. The role is permanently encoded as a specific physical coordinate in the memory geometry. The verification runs on combinational logic. A single hardware XOR gate checks the address content correspondence. This occurs in a single O1 hardware cycle, fetching and verifying simultaneously. If the data drifts from its authorized role, its physical displacement instantly triggers a hardware-level halt. The XOR gate has no program counter, no loops, and executes no instructions. It operates in a lower computational class, making it structurally impossible for AI to hack. By separating the verifier into a lower computational class, the architecture bypasses the halting problem entirely. This is the reality for the general counsel, the chief risk officer, and every executive signing off on an AI deployment today. The European Union AI Act enforces its requirement for continuous anomaly detection, starting August 2, 2026. Relying on software layer wrappers to govern Turing-complete AI is legally and mathematically obsolete. The distinction between computational classes is established, public knowledge. Ignorance of this structural limit is no longer a viable defense in an enforcement action. Adopting substrate-level hardware verification converts AI deployment from an uninsurable liability into a measurable, actuarially sound asset. The next AI deployment you sign must be backed by the undeniable laws of physics, not the breakable promises of software.